Good evening, everyone. I hope I'm audible. I am Shreya, the TA for the course, and today I'll be discussing problems related to week 6 lectures primarily. I will discuss a little bit about week 7, and of course, one of the problems that I am yet to discuss. So, before proceeding, is everybody able to hear me and see the screen? Can you please confirm?
Yes, ma'am.
Okay. All right. So I'll just start with what was discussed in week 6. So in week 6, we learned a little about index numbers and why it is important to learn about them, because it gives a comparative measure, and it's very important in economics because of the constant changes in prices and uh, which leads to changes in values. So because of those reasons, like inflation and deflation, we have to adjust our calculations according to the rate or the current economic status of a country or a place. So for those reasons, it's very important to study index numbers. And we also saw what are the types of index numbers. So if I have a quantity whose price at tth time point and price at some base time point is given, then simple index number is nothing but the ratio of the two into 100. This was simple um, index number. And how did we what were the criterias that were specified for selection of base period? So there were two criterias primarily. The first one was that base period should not have abnormalities. And the second one was that it should be closer to the period of observation or inspection, you can call. So if I'm considering the inflation or the indices in this 2020 to 2030 decade, then a base year of 1990 would not make much sense. So I have to take somewhat a period which is closer to this time point. Is it okay?
Yes, ma'am.
So this was the criteria for selection of base period. So apart from these simple indices, which could be in terms of price and also could be in terms of quantity, also could be in terms of value. So this thing, any index number could be with respect to price, with respect to quantity, or with respect to value, which is nothing but price into quantity. Okay, and then we moved on to discuss what was known as a composite index numbers, and there we discussed simple aggregative indices, and here we discussed something known as value index. So what was that? It was if I have, let's say, the price figures for one time point and the quantities for one time point and the price and quantity for a base time point, then summation P1 Q1 T by summation P0 T Q0 T. This was my value index. Value comparing the tth time point to the base point. Apart from this value indices, we learned about some simple aggregative indices, which would be addition of the price indices at the point of inspection by the total price indices in the base year into 100. Similarly, it could be quantity summation Q1T summation Q0T into 100. Instead of the aggregative indices, sometimes we also use the average of relative indices, and that is calculated as summation P1T by P0T. That is, we calculate something like this, the relative indices, and then we take a sum. So, or in other words, we take an average by the total number of commodities that we have in our basket, and that is expressed in terms of 100. Okay, so we learnt about this thing as well, and apart from this, we also learned about weighted average of relative in price indices, or it could be quantity indices as well. So in that case, what did we do? As an illustration, it was shown that the weights could be the value at the base year. So this one was referred to as weighted average of relative price indices. Was nothing but summation P1T by P0T, the relative price indices, into some weight divided by the total summation weights into 100. Now the weights could be anything. One choice of the weights is the value at base year, that is Pi naught into Qi naught. So if we substitute Pt naught, Qt naught, let's say. So if we substitute this thing here, then essentially we'll land up at the Laspeyres price quantity indices. Okay, so this one, with this choice, the Laspeyres price or quantity index given by LP was nothing but summation P1T. Anybody else? Okay. So it was P1T into Q0T by summation P0T into Q0T. So here the weight, the price indices, the simple aggregative price indices are weighted by the quantity at base year. Similarly, if we compute the Pache's price index, then let's say this is, then LP would be summation of P1T at current quantity by P0T Q1T. And Fisher's price is nothing but geometric mean of the Laspeyres and Pache's index into 100. Okay, this was discussed regarding index numbers. And then we proceeded to the discussion in the context of time series. So if I, let's say if I have a time series like this, then we see that there is a long term trend component. Few, let's say this is monthly data, Jan, Feb, then again this is Jan, Feb, and so on. So every Jan, Feb we see some repeating patterns. So the smooth long term movement of a series observation is nothing but the trend. And these fluctuations, periodic fluctuations or repeating patterns with a period usually less than a year, though these components are known as the seasonal component of a time series. Now if we see some pattern repeating over large amount of time, so let's say if we have some data, this pattern, this one, let's say this is year 1, again we have something like this, year 2, and so on. If this same pattern repeats over 10, 5 to 10 to 20 years, then that is known as a cyclical component. And apart from these three form the non-stationary part of a time series. So apart from these non-stationary components, there could be a separate totally random component that could be the something, if we assume that this is totally random, it could be white noise or purely a random variable generated from a normal distribution. So these fluctuations are essentially these trends, seasonality, cyclical movements. These patterns are somewhat definitive. And it's important to model these and remove these components to finally model the residual random component that is there in our time series. So two kinds of models we learned about. One was the additive model and one was the multiplicative model. So the additive model was trend plus seasonality plus cyclical component plus irregular component, or this is the random one. So mostly this model is preferred when, so here in the classes it was assumed, and it is normally assumed, since this cyclical component it requires a long period of time, this is mostly assumed to be 0. So these additive models are usually fit in the absence of cyclical patterns. It is fit when the seasonal fluctuation remains same across different time periods. For example, if YT denotes the consumption of, let's say, electricity, so these patterns remain more or less constant each year. In winters there will be some pattern, in summer there will be larger let's say amplitude, if amplitude is equivalent to the total units of electricity consumed. So it can be assumed that during the winter months every year across different time periods the consumption of electricity has the same pattern. So in such cases it will be wise to use an additive model. But in cases when the seasonal fluctuation is also varying across some time levels, then it would be wiser to use a multiplicative model. So a multiplicative model would be something like this. Okay. Then we learnt about concepts related to trend estimation. So for trend estimation, we learned about fitting least squares, then calculating moving average, which would give an estimate of the underlying trend. So moving averages could be centered moving average or weighted moving average, where the y values are weighted with some w values and then the averages are taken. Could be a 3-point, could be a 5-point, or anything. And we also learned about something known as exponential smoothing, where the forecasted value at t plus 1th time period will be alpha into the observed value of the series at tth time period plus 1 minus alpha into the forecasted value at tth time period, where this alpha would lie between 0 and 1. And as a metric of the accuracy, we learnt about mean absolute error and mean squared error. Mean absolute error would be yt minus ft, and mean squared error would be yt minus ft whole square. So these were the concepts that was discussed. So now we'll solve a few problems related to these concepts. Okay. Any doubts so far? If not, then I'll proceed. Okay. Okay, thank you. So the first question is, find out the index value by price relative method for the year 2007 from the following data in table 1. So here what we have is the prices of 1, 2, 3, 4, 5, 6, 7. So if these are my items, I have 7 items in total, and their prices in 2004, we can assume this to be our base price, and prices at 2007, this can be our current price. So here we have 100, 100, 10, 9, 5, 4, 4, 2, 1, 1, 2, 2.50, 3, 2.25. Okay, so the relative prices would be price index would be this. So this would be 100 by 100 into 100, that is 100, This would be 9 by 1 second. This would be 9 by 10 into 100, that is 90. This would be 4 by 5 into 100, that is 80. 2 by 4 into 100, that is 50. 2.5 by 2 into 100, that would be 125, and this would be 2.25 by 3 into 100, this would be 75. Now the index value will be 1 by n. So the PT that we want is 1 by n summation of P1 T by P0 T into 100. So this will be 1 by 7 into sum of all these, 100 plus 90 plus 80 plus 50 plus 125 plus 75. So how many did we get? 1, 2, 3, 4, 5, 6. There should be one more. Okay.
1 upon 1.
1 upon 1, yes. So this was 100. Okay. So then if we calculate this thing, how much is the price index coming? If we add everything, this is 620 by 7. It will be 88.571. So option A is the correct answer. Is it okay? Shall I move on?
Yes, ma'am.
Okay. So question 2 is that from the following price quantity information obtain Pache's index price index for the year 2004 with 2000 as base year. So this is the price and quantity information. So this is price in rupees per kg, year 2000, which is the base year, and this is 2004, which is the current year. Quantity also, this is Q0, quantity for base year. Q1 is quantity for current year. So then the Pache's index would be summation P10 into Q10. Quantity at, it will be weighted at current price, current quantity. It's price index, so this will be weighted at current quantity. So what we would have essentially is P1I Q1I divided by summation P0I Q1I. So this will be P1 into Q1, 5 into 120 plus 70 into 130 plus 40 into 70 divided by P0 into Q1, that is 4 into 120, 4 into 120 plus 60 into 130 plus 35 into 70. So this will be 600 plus 9100 plus 2800 divided by 480 plus 7800 plus 2450. So this will be 00951 12500 divided by 0 5 0. This is 3. I'm sorry. This is 3. Is it okay? So this one divided by this will be 0.85. Sorry, opposite 12500 divided by this will be 1.1649 into 100. So everything into 100 we would have here. Here also this one into 100 would be, the answer would be 116.495 something. So it will be 116. Is it okay? Since we are having purchase price index, we'll weight by quantity at current year. Similarly, if we would have wanted last year's price index, we would have taken the quantity at base year. Is it okay? Any doubt? All right. So then I'll move on to the next one. So suppose cost of this commodity is increased by 50%. However, Azim maintained its former scale of internet consumption, which increased his cost of living by 5%. Then what percentage of his cost of living was due to using 4G internet before change in cost? So if we have our basket like this is 4G internet, and others. Let X be the consumption. Let total consumption be 100. So if X percentage is the if Azim uses X percentage of his cost of living, then this would be 100 minus X. And prices have increased. Let's say if increase in price, if this is 50%, or let's say if we model percentage increase in price, then this is something which we'll call I, and the consumption is something we'll call weight. So summation IW will be 50x into 0. So cost of living index is given by summation index into weight divided by summation of weights. So this will be 50x divided by 100. Now this value by the problem, this 50x by 100 is equal to 5%. That is, no, this is 5 because we are modeling by percentage. So then X would be 500 by 50, that is 10% or 10. So the answer is 10%. Is it clear?
Yes, ma'am.
Okay. So this problem states that the GDP data for different quarters of 2010 is as given below. So based on this information, we have to calculate the projected values for 2010 Q4 following exponential smoothing method. Now we have 4 data points. Let's say 2010 Q1, 2010 Q2, 2010 Q3, 2010 Q4. So the values are somewhat like this: 06.46, 1129.18, 1232.24, 1322.96. So if alpha is 0.2, then we know at t plus 1th time point it will be alpha t plus 1 minus alpha ft. So F1 will be Y1 for simplicity. Sorry, F2 we would keep as Y1. So this one would be 1106.46. For this one, it will be 0.2 into 1129.18 plus 0.8 into 1106.46. This would come out as this would be something like 111.004. 1111.004. This will be the projected value for quarter 3. For quarter 4, what will be the projected value? It will be alpha into this quarter one two 32.24 plus 0.8 into 1111.004. So this will be so this will be 1135.2512. So the projected value for Q4 is 1135.251. Is it okay? Shall I proceed? Okay. Okay. So using table for information, compute the trend for 2010 using a 3-year moving average method. So here we have how many data points? 1, 2, 3, 4, 5, 6, 7. So 7 data points. 7 is odd, so no need for centering. So we'll just plot the time points 2005, 2006, 1, 2, 3, 4, 5, 6, 7, let's say. So this is 2, 4, 5, 7, 8, 10, 13. So first we will take these 3 points and write in the center. This will be 2 plus 4 plus 5 by 3. So this will be 3.67. For the second point, we will leave out the first one. Compute moving average for these 3. So this will be 4 plus 5 plus 7 by 3. This would come out as 5.33. Then we leave this one out. These three together. 5 plus 7 plus 8 by 3. This would be 6.67. Then we would leave this one out. 8 plus 10 plus 13 by 3. This would be 10.33. Now the question is trend for the year 2010. So whatever is aligned with 2010, that one we are going to take. So then the answer is 10.33. Is it okay? Okay. So we'll proceed to the next one. The following table provides data on monthly import of raw jutes from 2016 to 2019. So given the information, compute the adjusted seasonal index for the month of February. Okay, so the first task is to compute a 12-point seasonal index. So how do we do that? Let's say this is sorry. Okay. So let's say this is month and this is the value. So this is 103.4. This is 105.6 and so on and so forth. 89.5. So just to save some time, I've already computed this thing. Okay, so first we'll try to understand what is happening over here. For the timing, let us forget this one. Okay, so what is happening is that we have the values for these many months. So the first step is to calculate a 12-month total. So we'll take sum of all of these together and align it to the midpoints. Okay, so this value is 103.4 plus 105.6 plus 89.5 plus 69.2 plus 55.6 plus 48.7 plus 42.4 plus 47.8 plus 87.3 plus 100.9 plus 143.9 plus 138.9. So if we add all of these up, we'll get it 1033.2, and we are going to write it in the center. Like here we would write 1033.2. Okay. Similarly, if we leave these out, then this entire thing total is 1060, that we are going to write in the middle between July and August. Okay. Now once we have our all 12 point values like this, what we are going to do? We are going to take the average of 1011.2 and 1060, and that we are going to write for July. So if we do an average of 1033.2 and 1060, how much do we get? 1046.6. Okay. So then okay, so after calculating the total, if we do a 5-point average, these we are going to get 1033.2. 1033.2 divided by 12. How much will it come? It will be 86.1. So after calculating the month's average, we are going to get the moving average for the 12 months. So then we would write this as 26.10, this one would be 88.33, and so on. And then we would do a centering. Can you please check if this one is coming to 1033.2 or is it already centered? Okay, this is not centered. These are the midpoint values. So once we get the midpoint values, we are going to do a centering. Then 86.10 plus 88.33 divided by 2 would be 87.215. So then we are going to divide that by the value at this time point, that is 42.4. One second, what is coming? There is some problem here. There's some calculation mistake over here. I'll come back to this later then. Okay. So the basic idea is you calculate the 12-month total, get the 12-month average, center the values, divide it by the value at that current time point, and then you are going to get a table like this, which will have the last column as values over here. And then for each of the months we have to calculate the average index. So for February here, if these values are true, then it would be 127.8 plus 107.92 plus 105.65 divided by 3. So this would be 113.79, and so on for all of these. So this is what we would have for this point. For this point, the mean would be divided by 4, 49.25 plus 57.47 plus 65.18 plus 59.58 by 4. This would be similar to, this would be equal to 57.87. So for each of the months we are going to get an average index, and then we are going to add all the average indices up. So it will be 141.31 plus 113.79 plus 101.58 plus 80.83 plus 76.92 plus 60.79 plus 57.87 plus 62.88 plus 87.70 plus 116.11 plus 153.18 plus 158.12. So this comes up to be so this comes up to be 1201.08. So then the adjustment factor would be 1200 by 1201.08, and that is equal to 0.999. So what we are going to do, we are going to multiply these average columns into the adjustment factor. So here this would be, for Feb it would be 113.79 into 0.999, and that would be 113.67 or approximately 113.7 as it has been written over here. So for April it would be 80.83 into 0.999. So it would be 80.749. Okay. Here some more decimal places were also there. So this is how we should calculate the seasonality indices for a particular month. The important thing here is to get the adjustment factor, because the sum of all these indices should be 1200. Similarly, if we have quarterly data, then the sum should be 400. So we should add up everything and adjust by factor 400 instead of 1200. Is it okay? Alright, I'll move on to the next one. So the following are the group index numbers and group weights of an average working class family's budget. So we should construct the cost of living index by assigning the given weights. So this is index number I, and this is what we mean by weights. So cost of living index is given by summation IW by summation W. So if we have one more column like this, IW, then this will be 352 into 48, 220 into 10, 230 into 8, 160 into 12, 190 into 15. So then summation IW will be So this one, the total comes up to be summation IW is 25706 divided by summation W is 93. So then cost of living index will be 276.408 or 409, approximated by 276.41. I hope this is clear. Okay, so I'll move on to the next one. So here they are saying the annual production of a commodity is given as follows. This is the production values in tons, and they have asked to fit a straight line trend by method of least squares. So we want something like yt equal to beta naught plus beta 1t plus epsilon. We want to fit this regression model by the method of least squares. Now how will I devise my table? So this should be time point 1, 2, 3, 4, 5, 6, 7. Okay. So if we have to fit a trend by the method of least squares, we have to minimize sum of squares of errors. So we have to essentially minimize this quantity. Now how am I going to do this minimization? So to minimize, what we'll do, let this be the sum of squares of errors. We'll do del s. So we have two unknown parameters, beta naught and beta 1. So first we'll do del s del beta naught, equate it to 0, and then we'll do del s del beta 1, equate it to 0. So then we have two equations in two unknowns, and from there we can get beta naught hat and beta 1 hat, which will be the estimates of the regression line. Okay, and if we do, so the method of OLS is designed in such a way such that if we do the second order derivatives, then if we remember this h minus, so in second order, so in 1D there is this concept that if we just do ddx of some fx to 0, and then the double derivative, if this is less than 0, then this point, wherever it is, this is the maximum. So similar extensions we have if we have for two unknown variables. So without going into too much of details, what we are going to do is that we are going to take this sum of squares. We are going to partially do partial derivatives in terms of beta naught and beta 1, equate them to 0 and get the values of beta 1 and beta naught. So if I do this, then what am I getting? Del s del beta naught will become summation, this 2 will come previously in front, 2 yt minus beta naught minus beta 1t, and then chain rule. The coefficient of beta naught is minus 1. Here beta naught is the unknown. So we'll equate it to 0. Similarly, for this one, we'll have this 2 will come before, yt minus beta naught minus beta 1t into beta, the coefficient of beta 1 is minus t. So by chain rule that will also come. Okay, so these two are what we call normal equations in a regression setup. So if we solve the first two, then what am I getting? Summation yt minus beta naught minus beta 1t equal to 0. This summation is over t, this we should remember. And here we are getting yt, here we are getting tyt minus t beta naught minus beta 1t square equal to 0. Okay. So I'll write these two equations once more. Tyt minus beta naught t minus beta 1 t square. So if we separate this equation, we can write summation yt minus, let n be the, let t run from 1 to n. So since this term is free of t, we can write n beta naught minus beta 1 summation t to 0, and this equation we can write summation tyt minus beta naught summation t minus beta 1 summation t square equal to 0. Now we are going to multiply this equation with summation t and multiply this equation with n. So then what are we getting? We are getting summation yt into summation t minus n beta naught summation t minus beta 1 summation t whole square equal to 0. This is equation 3. This is summation tyt minus ntyt, n beta naught summation t minus n beta 1 summation t square equal to 0. This is equation 4. So if we do equation 3 minus equation 4, then what am I going to get? If I take this to the right hand side, or I'll just do a plain and simple minus, then summation yt summation t, this one and this one is going to cancel, minus beta 1 summation t whole square minus n summation t by t plus n beta 1 summation t square equal to 0. So if we take the beta 1 terms to the right, then what we are going to have is that n beta 1 summation t square minus beta 1 summation t whole square equal to summation yt summation t or some mistake I did in minus. 1 second. This one minus this one, so this will become plus. This will also become plus. So plus nb t1 square minus b summation this equals to this one, this one. So this minus this one will become n, yes, will become, sorry, this will become n summation t by t minus summation yt summation t. Okay. Alright. So if I expand this thing, what am I going to get is that, so in the right hand side I have n beta 1 summation t square minus beta 1 summation t whole square equals to n summation yt into t minus summation yt summation t. So if I divide the n, both the sides by n square, what we are going to get? Beta 1 summation t square by n minus summation t by n whole square equals to 1 by n summation ytt minus summation yt by n summation t by n. So then beta 1 will become, this one we can write as 1 by n summation yt into t minus y bar into t bar divided by summation 1 by n t square minus t bar whole square. So if we do a little bit of rearrangement, then what is essentially comes to is the regression coefficient, that is summation t minus t bar into yt minus y bar by summation t minus t bar whole square. So this is the OLS estimate of beta 1. Okay, and if we substitute the beta 1 value in any of the normal equations, let's say I substitute beta 1 in the first equation, that is summation yt minus beta naught minus beta 1 minus beta 1 t, this is 0. So if we give beta hat over here, then what we are going to have is that summation yt minus n beta naught minus beta 1 hat summation t equal to 0. So then beta naught would become 1 by n summation yt minus beta 1 hat 1 by n summation t, which is nothing but y bar minus beta 1 hat t bar. So this will be the beta naught OLS, y bar minus beta 1 hat t bar. Okay, so this is how the ordinary least squares are calculated. The main thing is we write the sum of squares of errors, differentiate with respect to the unknowns, get the normal equations, solve the normal equations and get the values of the parameter. Okay, so then we have arrived at this final formula. I'll just write it in a proper slide. So if yt equals to beta naught plus beta 1 t plus epsilon was my model, then the OLS estimates are of beta 1 hat is this one, yt minus y bar into t minus t bar by summation t minus t bar whole square, and beta naught hat would be y bar minus beta 1 hat t bar. Keeping these in mind, now we are going to fit a linear trend using these information. So what we have, t, year and y. So this is 1995, 1996, 1997, 1998, 1999, 2000, 2001. So T will code as 1, 2, 3, 4, 5, 6, 7. And the Y's are 155, 162, then it is 171, 182, then we have 158, 180, then we have 178. So now we are going to get t bar. T bar is how much? 1 plus 7, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 by 7. So t bar will be 7 into 8 by 2 divided by 7. That is 4. This formula is if we add 1 to n, then this would become n into n plus 1 by 2. Here n is 7, so it will be 7 into 8 by 2, the total. And then since we need average, we are dividing the total by 7, so that is coming out to be 4. So now if we have a column t minus t bar, this one would be 0, this would be minus 1, 1, minus 2, minus 3, 2, 3. And y bar would be 155 plus 162 plus 171 plus 182 plus 158 plus 180 plus 178 divided by 7. So this would come to 169.428, approximately 169.43. So then we would get one column y minus y bar. So this will be 155 minus 169.43. Then this would be 162 minus 169.43. This will be 117 minus 169.43.
1000.
This will be 182 minus 169.43. 158 minus 169.43. 180 minus 169.43. 178 minus 169.43. So once we have these two columns, then we are going to get one more column additionally, and that will be, so now we have something like t, y, t minus t bar, y minus y bar. So then this column, the next column would be t minus t bar into y minus y bar. So if we do this was something 155 minus 169.43. Something this would have been 155 minus 169.43. This is minus 14.43. So then this column would be 14.43 into 3, that is 43.29, and so on. So then we would take this column and t minus t bar whole square. So this was minus 2 minus 1 0 1 2 3. So we would have 9 4 1 0 1 4 9. So this will be 13 plus 1 14 14 28. And we would have something t minus t bar y minus y bar. And then finally beta 1 hat would be summation t minus t bar y minus y bar by 28. So the calculation is this. Where is that? So this is t, this is y. This column is y minus y bar. This column is t minus t bar. This is y minus y bar into t minus t bar. This is t minus t bar whole square. So this quantity is summation y minus y bar into t minus t bar, and this quantity is summation t minus t bar whole square. So beta 1 hat is 92 divided by 28, which comes out to be 3.285. Is it clear? Okay, so once we have beta 1 hat, then beta naught hat would be y bar minus beta 1 hat into t bar. Then here y bar is 169.43 minus 3.286 into 4. Then we would get this as 156.286. So then if I go here, we were asked to fit a trend line. Where is the question? So this was the original question. So now my beta naught hat is 156.286, beta 1 hat is 3.86. So the predicted trend line that could fit this curve would be 156.286 plus 3.86t. So this is my trend equation, the required trend equation. Is it clear? Okay. So this OLS is nothing but the module that we are going to discuss next, or some parts we have discussed before. This is what we call a simple linear regression equation, or the classical linear regression model that we are going to have in the week 7 module. Okay, so this is the basic thing. What we are doing essentially here is that we are we have a set of data points, one like this. What we are doing, we are trying to fit a linear line such that these distances, the vertical distances, so this is my observed, let's say this is yt, and this is t along this axis, this is yt along this axis. Instead of t, now we can also write it as x, where x is my independent variable and y is the dependent variable. So what we are essentially doing from the scatter plot, we are trying to, this area is y minus y predicted. This is observed y, this is the predicted y. We are trying to fit this y hat as something beta naught hat plus beta 1 hat x, such that the error sum of squares is reduced or minimized. And how are we doing it? We are taking this form, we are differentiating with respect to the unknown parameters, equating them to 0, solving the equations and getting the values of beta, the estimates of beta naught hat and beta 1 hat. Okay, so we'll do one more sum on this thing so that it is clear. Okay, so let's say we have these values given to us. We have some x, x1, x2, xn, and some y's, y1, y2, yn. Okay, these observations are given to us. So x is nothing but process temperature and y is density. So here from these x's and y's, we have these values calculated. Okay. Now assume a simple linear regression model of type y equal to beta naught plus beta 1 x plus epsilon, and we have to find the least square estimate of beta naught and beta 1 and the coefficient of determination, that is r square. Okay, so how are we going to do this? So we saw how beta 1 and beta hat is calculated. So beta 1 hat is summation yi minus y bar xi minus x bar divided by summation xi minus x bar whole square. Note here that in the previous case, instead of x we had t. The time we had modeled as 1, 2, 3, 4 something. So the same thing, we'll just replace t by x and we have this beta 1 OLS estimate. So this will be, the value is already given, 80 divided by summation xi minus x bar whole square, that is 160. So we have half. Okay, so then beta naught hat will be y bar minus beta 1 hat x bar, then that is 3 minus half into 5, that is 3 minus 2.5, 0.5. Then the fitted equation is y hat equals to 0.5 plus 0.5x. This is the fitted linear regression equation. Any doubts? So I hope you will be able to solve problems. If x's and y's are given to you, you'll be able to get the estimates and write the normal equations. Okay, so once this is done, the next thing is to find the coefficient of determination. Now, yeah, any questions? Okay. So the coefficient of determination r square is actually the variance explained by y hat, or this is the ratio of variance of y hat divided by the variance of observed y. Now this can be written as sum of squares due to regression by total sum of squares. Okay, so if you remember, in ANOVA as well, we split it, the total sum of squares were split into sum of squares due to treatment plus sum of squares due to errors. So this is nothing but a special case of a regression with dummy variables. Okay, so here also in regression analysis, we have the sum of squares total. This can be also represented as sum of squares due to regression plus sum of squares due to errors. Now this r square is nothing but 1 minus sum of squares due to errors by sum of squares total. So SSE is nothing but summation yi minus yi hat whole square, and SST is summation yi minus y bar whole square. So from these two, so in the form of a table, if we write anything, if raw x and y values are given to us, then we can easily fit the equations. We can find out these values. Okay, we can get beta 1 and beta naught, and then we can find out y hat. Once we have y hat, we can just take the differences between the predicted or estimated y and the observed y, get their square, and calculate these figures as well. Okay, but it can be shown, and I am not showing for the interest of time. It can be shown that sum of squares due to regression is beta 1 hat square into okay, so this is nothing but beta 1 hat square summation xi minus x bar whole square by summation yi minus y bar whole square, and summation due to errors or summation due to residuals. So this quantity that we have yi minus y hat, this is what we call it as a residual. So this, it will be wise to call it sum of squares due to residuals. Okay, so then total sum of squares can be split into sum of squares due to regression plus sum of squares due to residuals. Now, as I was saying, sum of squares due to residuals can be then written as sum of squares total minus beta 1 hat square summation xi minus x bar whole square divided by summation yi minus y bar whole square. Okay, so here we have r square. R square is sum of squares due to regression divided by sum of squares total. So we'll compute, or this can also be equivalently written as 1 minus sum of squares due to residuals by sum of squares totals. Okay, so ultimately it will boil down to this formula. So first let us compute what is the sum of squares due to regression. Here beta 1 hat we got as half. Summation xi minus x bar square was 160. Summation xi minus x bar square was 160. And summation yi minus y bar square was 83.2. So then this quantity, sum of squares due to regression, is 1 by 4 into 160 divided by 83.2. So this will be 40 by 83.2. So then r square equal to I'm sorry. 1 second. Yes. I'll write it afresh so that it's clear. I'm really sorry for this. Okay, I hope this still here it's clear to everyone. What do we mean by r square? R square is sum of squares due to regression by total sum of squares. Now here sum of squares due to regression is written as beta 1 square sxx. Summation xi minus x bar whole square. So then r square will be sum of squares due to regression by sum of squares total, which will be beta 1 hat square summation xi minus x bar whole square divided by summation yi minus y bar whole square. Okay, so then we have here, we had beta 1 hat as half, xi minus x bar whole square was 160. and yi minus y bar whole square was 83 point, what was the value, 83.2. So then r square would be 1 by 4 into 160 divided by 83.4, that is 40 by 83.2, which will be 0.48. So the interpretation is that, how do we interpret r square? We interpret that 40% variation in y is captured by this regression equation, or in other words 48% of variation in y is captured by y hat. Okay, because r square is nothing but the proportion of variance of y hat divided by variance of y. So the closer r square is to 1, the better is my regression fit. Is it okay? Just to give a brief recap, here if we have x and y values, x1, x2, xn, okay, and if we have y1, y2, yn, we'll have to compute beta 1 hat, beta naught hat. From there we can get the sum of squares due to regression, sum of squares due to residuals, sum of squares total. R square would be sum of squares due to regression by sum of squares total. And we can also conduct test of hypothesis to check whether my x variable is significant or not. For that we can also construct a table, but these things will follow similar to an ANOVA table. And then if we do MS regression by MS residuals, that will be an F test based on the corresponding degrees of freedom. And if the F observed is greater than the F cutoff, we are going to say that we are going to reject null and say that yes, x variable is significant. Okay, but for all of these things we have to first compute beta 1 hat, beta naught hat, get the sum of squares due to regression, sum of squares due to residuals, and also remember that total sum of squares is partitioned into sum of squares due to regression plus sum of squares into residuals. And for a simple linear regression where my x is, I only have one independent variable, the sum of this one will be 1, the degrees of freedom will be n minus 2, because total degrees of freedom is always n minus 1. And then we know how to calculate MS regression, SS regression by degrees of freedom, that is 1, MS residual would be SS residuals divided by n minus 2. Then we get the observed F statistic, calculate it with the critical point at alpha level of significance, and the H naught is beta 1 0 versus beta 1 not equal to 0. Okay, so these things will follow later, and in the next class we are going to solve more problems on the CRLM models and equations. Is it okay? Okay. So this is what I have for today's session. For the last week's session, there was one sum which was left and which was not discussed yet. So I'm just going to discuss this and then we'll end the session. So this was a problem related to ANCOVA. Why this is an ANCOVA problem? Because we have a covariate term in our model. So if y is my dependent variable, there's some baseline thing, then we have the main effects due to one variable plus, let's say, uh, main effects for the other variable, and some interaction terms maybe, and then we would have something gamma j into xj plus epsilon. Okay, so this is a very crude format I'm writing. So here this all of these are can be coded as dummy variables as we have seen in the class, and then we can use the regression model with these dummy variables to get the estimates and sum of squares of all of these, and then finally get the mean square. Okay, so first thing here the question asks is that based on the information given, compute the residual sum of squares or residual mean square. So as we know, in any ANOVA or ANCOVA or regression model, the total sum of squares is partitioned into, let's say here we have SSA, SSB, SSAB plus SS covariate plus SSE, something like this. So entire this thing is my sum of squares due to model. So from here we can see that the model sum of square is 163.505. Therefore, the error sum of squares or residual sum of squares would be the total minus the model sum of squares. So it would be SSR would be 185.867 minus 163.505, and this would come out to be 22.362. Okay, and here we have been given what will be the degrees of freedom. So the degrees of freedom is 23. Therefore ms would be 22.362 by 23, and this would be 0.9722. 0.972. Okay, I hope this is clear. So now if we have to find out from the given information, is there any significant effect of the covariate term, then what we are going to do? We are going to do an F-test on the covariate term. And how am I going to do that? I am going to take the ms covariate divided by ms residuals and then compare it with the F critical value. Okay, so if we go to this slide, we'll see that the degrees of freedom of the covariate is 1 and the mean squared error is 0.838. So then we have 0.838 divided by 1 by 22 point, what was the residual error? 22.362, and the degrees of freedom was 23. 262 362 divided by 23. So this comes out to be 0.838 divided by 0.9. How much was it? 0.972. So this comes out as 0.862. And then we are going to compare it with the F critical value. So the degrees of freedom of that F distribution will be degrees of freedom of numerator, degrees of freedom of denominator, and the upper 0.05 value. So this value is somewhere close to 4.27. Okay. So if I have this distribution above 4.27, this area is 0.05. So my H naught was, if let's say gamma is the term for is the effect of covariate term. So then H naught was gamma equal to 0 versus gamma not equal to 0. Now since here in this F test we see that, and the rejection rule was reject H naught if and only if F observed is greater than F critical. Okay. So here we see this one is less than 4.27. Hence, we do not reject H naught and conclude. What do we conclude? Is there any significant effect of the covariate term? No. No significant effect of covariate. Is it okay? So even if I have a regression model, so the same thing like an ANOVA table, here also for a regression model we can also have an ANOVA table where we would have sources of variation. This would be the regression and this would be error. This would be total. Then sum of squares due to regression, sum of squares due to residual, sum of squares total. Then degrees of freedom, this would be 1. This is for a simple linear regression. What do we mean by a simple linear regression? Only one independent variable. This sort of a thing. If there are multiple independent variables, like more than one axis, then that will be a multiple linear regression, and then the DFs will sort of change. Okay, but for the time being, we'll just concentrate on a simple linear regression, and the degrees of freedom will be 1. This will be n minus 2. This will be n minus 1. So then we would have MS regression, MS residual, and to test for H naught beta 1 equal to 0, we would use MS regression by MS residual. This will be the F observed, and the rejection rule will be reject H naught if and only if F observed is greater than F1 n minus 2 0.05. Okay. So for a simple linear regression, the test for significance of the regression line boils down to beta 1 equal to 0. This is not true for multiple linear regression. Okay, so whatever I am saying in this slide is in the context of a simple linear regression. Okay. Okay, then I'm done for today's session. If there's any problem, you can ask me now or you can ask me later, and We'll meet again next week. Any doubts you can ask me. Doubts, comments, feedback.
Thank you, ma'am. Thank you.
Okay. Thank you then. See you next week. Bye bye.